Now we want to look at one of our first methods, one of the easiest methods, in fact. And if I were making a list, this would be number one on that list: separation of variables. So I want to take a look at 3 examples using this method to solve a differential equation. Our first problem, dx dy equal to 1 plus 2y squared over y times sine of x. So the first thing I look, and I know this is a little different because it's dx dy, not dy dx, so we're so used to from calculus. But the first thing I notice is that I can separate, thus the name of the method, I can separate the variables x and y. So let's separate them. So I'm going to take the sine of x over, and I'm going to take the dy over. So now I have separated the y's and the x's. Now let's simplify this right-hand side a bit. So this would be dy over y, and this would be plus 2y dy. Now what can I do? Now that I have this variable separated, I can integrate both sides. So I will integrate that. Integrate, of course, the integral of a sum is the what? The sum of the integrals. So that's exactly what I can do. So what do I end up with? Well, the integral of sine of x dx, of course, would be what? Negative cosine of x, and I'm going to go ahead and put the plus c on this side. It does not matter which side I put the plus c on. Now, what is the integral of dy over y? Well, of course, that's ln natural log of y. Next, 2y dy. What's the integral of 2y dy? Well, that would, of course, be y squared. So there is my solution. My solution is negative cosine of x plus c equal natural log of the absolute value of y plus y squared. Now notice, I did not solve for y. Implicit is fine. In fact, this would be very hard to solve explicitly. Now let's look at our next example. E to the x plus e to the minus x dy dx equal to y squared. This one's easy to see that I can separate the x's and y's. And so that's what I will do. So this becomes dy over y squared equal to, flip, so this becomes dx over e to the x plus e to the minus x. Now, I can easily integrate this left-hand side. It's the other side that needs a little manipulation. So let's manipulate it. So the first thing I'm going to do is I'm going to take this e to the minus x and I'm going to make it into a fraction. So this would be dx over e to the x plus 1 over e to the x. Well, let's get a common denominator. So that'd be e to the x. So what do I get? I'm going to get, in the denominator, I'm going to get e to the x quantity squared plus 1 over e to the x. Well, if it's in the denominator of the denominator, it flips. So it comes up here. E to the x dx. Well, if I were to use u substitution, where u is equal e to the x, so du is equal e to the x dx, this becomes du over u squared plus 1, which I recognize from my inverse tangent. So integrate both sides. And so what do I get? I get from the integral of dy over y squared, I get negative 1 over y, okay, equal to, again, this is inverse tangent of what, though? This is inverse tangent of e to the x. And then I'll write plus c. Again, I'm going to leave it in implicit form. My third and last example, e to the negative y plus 1 times sine of x dx equals 1 plus cosine of x dy. And this time I'm dealing with an initial value problem, an IVP. I'm going to have y of 0 equal to 0. So again, let's separate. Well, this one's easy to separate. So let's divide everything by the 1 plus cosine of x. So I get sine of x dx over 1 plus cosine of x. And then let's divide everything by e to the minus y plus 1. So I get dy over, and I'm going to write it 1 plus e to the minus y, which of course I'm going to do the same thing that I just did over here with the e to the y, so that would be e to the y dy over e to the y plus 1. Again, all I did was make this 1 plus 1 over e to the y, and then I get a common denominator, and the denominator of the denominator comes up on top. Now, let's integrate both sides. Well, on this side, what do I have? Well, let's let u be 1 plus cosine of x. So du is negative sine of x dx. So on this side of the differential equation, what will I get? I'll get negative natural log of absolute value of 1 plus cosine of x. On this side, I'm going to let u be e to the y plus 1, so du is e to the y dy. So, what do I get? I get, again, natural log of u. So this would be natural log of absolute value of e to the y plus 1. Now, I have not written my plus c yet. I notice I have natural logs here. So why don't we put a plus ln of c, just to make it easier so that I have all natural logs. So what do I have here? Let's put this with this one, and let's take this one over to the other side. So I'm still going to keep it a positive because it's an arbitrary constant. Positive or negative arbitrary constant is still an arbitrary constant. So I'm going to have natural log of absolute value of e to the y plus 1 plus the natural log of the absolute value of 1 plus cosine of x. Well, this, using the properties of natural logs, becomes what? The natural log of e to the y plus 1 times 1 plus cosine of x. I'm going to drop the natural logs of the absolute values because I'm going to make everything the same, this arbitrary constant having the same sign. So basically, what do I get? I get c equals e to the y plus 1 times 1 plus cosine of x. Now, I've got my initial condition here. So what I want to do is I want to plug it in. So c equals, y is 0, so e to the 0 plus 1, 1 plus cosine of 0. And again, that's coming from the initial condition. So what do I get here? E to the 0 is 1, so I get 2 times 2, so that's 4. C equal to 4 here. So My solution, therefore, is 4 equal to e to the y plus 1 times 1 plus cosine of x. That's separation of variables. Step 1, separate the variables. Step 2, integrate. And it's the easiest of all the methods.